So today we're going to be doing a software engineering lecture. This is somewhat of an experiment, so I'm going to give you some backstory on why it's happening. So interesting note that in 2003-ish and earlier, 61A had 2 days a week, Monday, Wednesdays, of technical topics, and then Friday was always something else. Now, sometimes that was some social implications thing where we talk about the impact of computing. I mean, it's way before. I was like your age at the time. But they would talk about alternate topics, whatever it may be, get guest speakers, whatever else. But over time, 61A's content grew and grew until Social Fridays, as I believe they were called, disappeared entirely. So what I'm trying this semester is I'm bringing this back a little bit in 61B, where for 3 weeks I'm going to dedicate this class to these sorts of topics. So it'll be a different flavor of lecture. It'll be less technical. It's not going to be, we have this old computation problem, let's try and solve it together. It's going to be generally a little vaguer. Now, these are untested lectures. Maybe they'll be good, maybe they won't be, so do let me know what you think. So some motivation for today is that if you think about your education at Berkeley so far, doing programming, we've misled you a little bit. In 61A, a lot of the projects and homeworks were fill in the function, where there's already a function, you just have to write the code to make it do the thing. And that's great for learning how programming works, and even for finding and identifying subproblems, but it's not quite real-world coding practice, sometimes. Now in 61B, we've zoomed out a little bit, and we said we'd like you to build a class, say an extrinsic min PQ or whatever, and you're supposed to do it according to our spec. We kind of kicked off the training wheels on the projects as we went, taking away our autograder and so forth occasionally. But I think it's fair to say that everything we've done, even Project 2C, is all at a small scale. I mean, 2C, you're going to have this giant code base, but you're not touching most of it. Most of it's just mysterious. You can go look at it, but it's not really something that you have to interact with deeply. Now, because you've always been working at a small scale, you have built habits that may cause you great pain if you build your own projects or whatever else in the future. So in these lectures, among other things, I'm going to give you a sense of how you would deal with large scale, where you're trying to actually build huge systems from scratch, where you're designing everything. Though I will note that in lecture, it's actually very hard to do this, because it's tough to find something that's small enough to fit into lecture, but it's large enough to showcase where these issues are problematic. I gave it a shot with an exercise. We'll do it at the end of today's lecture, but we'll see. So Project 3, that's where you'll have some breathing room. This is after bare maps. This will be a chance for you to actually design something totally from scratch, and you will feel the pain of the complexity as you realize that you're boxing yourself into corner with short-sighted decisions. So I hope that these lectures help you at least in some vague way, but this is one of the very hardest topics to teach in computer science. 169 is another place where you can get a taste of this, or if you go and do internships. So we'll see how it goes. Now, I should note that these lectures would not be possible, or they wouldn't be nearly as good, if I did not have this book. So I had a former TA, Kay Osterhout, who was a grad student here, and her dad is a computer science professor, as it happens, and he wrote this book. So if you want to check it out, I think it's pretty good. It's very high level, though. It's a high-level description of where you run into trouble, and so I'm borrowing heavily from this book. I want to give credit where credit is due. And it's a cheap book. All right. So let's try it out. So you've heard me say before that complexity is your opponent, your enemy in computer science. And so I'm going to try and define complexity, and I'm going to use John's definitions because I think they're pretty good. Now, funny story. Has anybody here ever heard of the text editor project that existed in 61B? Some of you. So at Spring 2016, we did a text editor project where I had you guys, as the big open-ended project, build a GUI-based text editor like Sublime Text, but much smaller. And these challenges, the ones where we have you build something from scratch, are all about you hitting complexity and feeling a little bad about it. Now, that project was particularly tricky, and since Kay was my TA at the time, she told her dad, who teaches software engineering, about this project, and so he ran it not in an intro course, but in an upper division software engineering course, and he found it very interesting to see the mistakes and strange errors and design decisions that people made in building their text editor. And in fact, indirectly, if you read in here, there's some talk about that text editor project, which is a descendant of our own. So we're kind of going full circle here. Anyway, so the point of this is he and I and others out there teaching computer science, we know that students grapple with complexity, and as a result of these kind of studies, not just the text editor project in his class, but his entire career, he's another generation older than me, he's come up with some definitions of complexity that resonated with me, but these are by no means universal. Okay. So to start understanding why complexity is such a special problem in computer science, that's actually kind of a great lecture for visitors, by the way. You don't have to know anything. All right, anyway. So unlike other engineering disciplines, like, I don't know, chemical engineering or whatever else, software is not constrained by physics. I mean, it is a little bit, because our computers only run so fast and have so much memory, but for the most part, you don't have to think explicitly about that. Now, as a result, when you try to build a system, when you're programming, it's an act of almost pure creativity. So chemical engineers, when they're dealing with building systems, they have to think about messy things like temperature. If I run these reactions, there's latent heat that gets built up, and I have to deal with getting rid of that heat. It restricts what you can do because there's physics. Material scientists, they have to think about how brittle a material is in order to recommend it for use in, I don't know, airplane window shades or whatever. And civil engineers need to worry about, say, the strength of concrete if they're building bridges. These things are very important, and they have to deeply understand them. And there's math where they deeply look at the properties, the tensile strengths of various materials. We don't really have that in computer science so much. We kind of do, but it's not nearly as deep and as reflective of some physical world that we're limited by. So instead, the limitation is not the materials that we are working with or the physical universe around it, but it's our own brains. It's the fact that we're not smart enough to understand really complicated systems. So the only limitation in terms of what you're capable of achieving is being able to understand what you're doing, which is a very unique and interesting space. Mathematics is kind of similar, right? Mathematics is a purely creative discipline, but it's not quite as directly applicable because there's no machine that brings to life what you're building. But in computer science, we have math that kind of lives. And now, in the modern era, of course, we've seen that it's very financially lucrative and impactful on society to be able to do this. Like, now that there's an internet, it's kind of insane how the mathematical ideas you come up with can deeply impact how people spend their time or what's going on in the world. So the limits of what it's possible to do at this point, especially now that we have the internet, is just what you are capable of fitting in your brain. So the enemy then is complexity. Our limitation is we are trying to understand the systems that we want to build, and what you'll observe, especially, so in this class, you usually build a program, you submit it to an auto grader, you make 30 changes, and you have git commits that are like, help, please, please, help, or whatever. And then you push it, and then you never touch that code again. It's very different than the real world. If you were to take those programs that you did that committing style with, they would eventually get so burdened and ugly under all those little changes you made that they become painful. So as programs are worked on over periods of months or years, which you never ever do in these courses, well, they gain more features and they gain more complexity. And over time, if you have a group of people working, it becomes harder and harder to understand what pieces you need to know about in order to make modifications. If you have hundreds of classes and they all interact in complex ways, then adding a new feature that, for example, lets the user, scroll around or something may be very hard. You don't even know where to start necessarily. Now, tools like IntelliJ, which we've used, or JUnit, or the IntelliJ debugger, or the visualizer, they make it easier to grapple with complexity. When you have it, you can use these things to extricate yourself from problems that you fall into. But actually, the most important thing you want to do in real software is to keep it simple. Okay? So let's try and define this a little more. So I'll start, I guess, just by mentioning ways that you might try to keep complexity under control. So one approach is to keep your code, well, as I said, simple, and what John uses the term obvious. So you don't want special cases. We saw that already creeping in early in our class when we were building S-lists. So we hit a case where there was a problem, where our code crashed and we tried to do add back, and we could add an if statement that handles the null root or a null front node case. Instead, we could also create a sentinel node. It's another approach. Another is encapsulation into modules. These are the two ways that he says you keep your code under control. So one is make it simple and obvious, and the other is encapsulate things. Put them in modules where you can hide information so that the creator of one module, let's say bare maps, can use other modules like KD tree or A-star solver or whatever else, and they don't have to know how they work. All they need to know is the API. These are incredibly important pair of practices that if you go do any real-world project, they will be the two techniques, the two levers you can use to keep things under control. This means there's less stuff to think about, and this means the things that you need to think about are small. They fit in our tiny working memories. So what is complexity then? How do you define this phenomenon? Well, Oosterhout defines it as follows. He says, complexity is anything related to the structure of a software system that makes it hard to understand and modify the system. So it's a human-centric definition. It's saying however hard it is for a human to deal with the system, to interact with it, to modify it, that's what matters. We don't really care necessarily how complicated it is just sitting on the shelf, but if we ever need to change it again, then that's where we're going to run into trouble. So complexity takes on a lot of forms. So for example, understanding how the code works. If you need to modify a piece of code, you have to be able to look at it and know what it's doing. It takes into account, for example, the amount of time you need to make small improvements. So like, oh, well, the font size sucks. I don't like it. How do I fix that? Well, in some systems, that's easy. There's some config file. I just change some number to 26 or whatever, and now it's bigger. In others, maybe you have to do something crazier, like go dig in the source code, modify a number, and recompile it, whatever it may be. Another is just being able to find what needs to be modified. I mean, that's closely related to the above idea. And another is if it's difficult to fix one bug without introducing another, which happens in code, where your code has so many interdependencies that changing anything breaks something else. So he goes on to say that if a software system is hard to understand and modify, then it is complicated. If it is easy to understand and modify, then it is simple. So he has a cost view of complexity, which is that, I mean, this is just another sort of, not a different definition, but a different way of thinking about complexity, is you can think of it as follows. In a complex system, it takes tons of effort to make even small changes, but in a simple system, big improvements require less effort. So I'm going to give you an example. You guys remember KD trees, Project 2B, and I gave you guys some pseudocode that looked a little like this. So we had a nearest helper method, and what it does is you give it a node, which is the root of a KD tree, or maybe a root of a subtree. We have a goal point, the thing we want to find, and we have a best point, which is our best known point. And the code is, this is the pseudocode as follows. So we say, if the node is null, we don't have anything better, so let's return best. Okay? If the distance to the goal from the current node is better than the distance to best, well, then I'm going to reset my best pointer. And then we're going to say, okay, we have a good child and a bad child, so we'll figure out which one's good and bad. Then we search the good and the bad child, and we return best. So this approach, I'd say, is simple in the sense that if you understand the pseudocode and you know the basics of 61B and you build code that looks like this, it's going to be relatively easy to work with. So question for you. Something's actually missing here. Okay, I'm going to let you guys try and find it. I'm not going to answer. See if you can find the thing that is missing. Yeah, I heard someone say it. Okay. Yeah, remember that pruning rule. So what's missing, let's see. Oh. Times are changing in Professor Hug's world. All right, cool. All right, so what's missing is what? The pruning rule. What do we need? We need to say what? So there should be an if statement here that I'm just going to write out in English that basically just says, if there could possibly be something better on the bad side, then do the search. Okay? Now, I've written this out narratively, but it is possible to write code that is reflective of this narrative. And that's the glory of programming, that it can actually read like a story if you do it right. So let me show you an example of a KD tree that is too complicated. This is not from any student this semester. In fact, it's from not even our class, but it's related. So here's a different way to implement the nearest method in a KD tree. So this is a little different than what we showed. It's not the same helper method. But just briefly looking at it, we can see that it is much more complicated. It's doing something kind of similar. So we have if is vertical, then do these things, otherwise do these things. There's a search here, and there's a check left variable. This is an else statement that has to do if it's not vertical. Well, in this case, we search, and then we say we should check the right. Then we have a check left variable. Then we go on to have some other stuff that if we check left, then if it's vertical, then we'll do Euclidean and so forth. And so, I mean, if you had to describe in a few words what feels bad about this, like what is, I don't know, I'm kind of curious how you would try and describe this in English. Sure. Yeah, there's a lot of redundancy here, right? Like this notion of check left, check right being set to true, like, I mean, at least it's narrative in the sense that we're specifying what it is we're going to do. It's not like do X or whatever. So I like the names, but there's some redundancy. Anything else? There are other ways you might put it. Yeah. Yeah, so it's hard to read, hard to say if it's correct. And so what about it? I mean, other than redundancy or any other phrasing about what feels bad about it? Yeah. Yeah, that's a really great point. If you wanted to expand this to a third, like you have X, you now have Z coordinates as well. Well, because we have this Boolean that is vertical, Let's say we wanted to now have 3 levels. Well, we could change that to an integer, but you can see this code won't generalize well. We would have to have an if statement for the x, the y, and the z, and so forth, and we would need to have God knows what. So it seems like it gets more complicated. Expanding on this code is nightmarish. Other thoughts that occur to you? Yeah. Yeah, so say you find a bug. This should be y and this should be x. I now need to go through every piece of code and swap that everywhere. And it's going to be really hard for me to keep track of it. Maybe by the time I get 8 lines in, I'm like, oh wait, should I have changed this one because it's a slightly different case than the one above. So this code is very hard to modify if you find there's any bugs or if you decide to make it better in some way. So for example, the pruning rule, in this case, it was basically just a line. And my KD tree solution looks almost like this, where it really is just an if statement somewhere that changes the behavior. Here, trying to get rid of the pruning rule is so complicated. The pruning rule, it's like roots all grown through it. This is like a weed, if you've ever dug them up in a garden where it's all like grabbing your actual plants. And you're like, oh God, what am I going to do? This plant's so cool, but there's this dandelion growing through it. I'm very upset about it. Like this, the pruning rule is baked into every aspect of the code. It permeates all of it, and that's dangerous. Any other thoughts? Yeah. God, it says verbose. Can you give me some examples? Yeah, it feels maybe a little strange to have check right and check left. And I think that's because of the framing or the abstractions that the author used, they were kind of stuck with them. But yeah, I agree. That seems like that's more stuff you have to keep track of. That if I'm using the debugger, now I have to need to think about this check left and check right variable. And it could have maybe just been called something like check other, or I don't know what. But probably downstream that becomes complicated. Interesting thought. Other thoughts? Yeah. Yes, so many cases, so many statements that it becomes hard to reason about. And indeed, yes, that's sort of redundant with the observation that it's redundant, but I think it's a great observation. Yeah. Yeah, trying to understand the intent of the author is really hard. If it came at this cold, here's a great example. Let's say that you're a TA at office hours, and somebody says, my code's not working. Here. And then they want you to start explaining the whole piece of code. We could do it, but it would take you perhaps an hour to explain what you were thinking. And if the problem is that you did this, there's no way that no TA will ever find that. It's not possible. Okay? That's another reason. It's hard to communicate, get help, whatever else. Yeah. There's little code coverage. What do you mean by that? It's not a term we've used. Yeah, so only some of the if conditions will be active at once. Why do you feel like that's a problem? Just to get some sense. So if you're trying to maybe identify errors or feel like it was correct, there's just so much to think about, so many different conditions that need to be considered. Great. Okay, these are all reasons. So this right here, you may have produced programs like this. It's fine. I've written terrible programs, especially when I first started writing code. And even now, I still produce code that's bad, usually when I'm in a hurry. And that's just how it goes. And we'll talk about that a little more. Here's another example of overly complex code. So this right here is a snap program. This is one of my former my former students in CS10. This is in the snap programming language. Who took CS10 here? Cool. Hi, friends. What's up? Anyway, so CS10 is your first dose of programming, and in that class, it is all about getting things just to work. So you've never seen this language, many of you, but I'll give you a sense of what's going on here that's surprising. So look at this. This is, even if you don't know the language, what seems maybe a little funny about this block of code? So it's an if statement, which is if this and this and this and this and this and not this and not this and so forth. Right? There's just a lot to look at. And you can imagine as a novice programmer, this is an implementation of the game Battleship. So it's like if ship hit is true and down is true and right is true and up is true and left is true and num is less than 91. Who knows what that means? That seems very hard to understand. Oh, and not. It's some item of official. It's hard to even imagine what it means, right? Now, this student, by the way, is now a 186 TA. So now 4 years later, they are graduating. They started here with this code. This is how they used to program. but now they're running a pretty sophisticated upper division course as one of the 20-hour TAs. So I bring this as an example up because in this case, this is not a large and sophisticated system. It's just complicated in the sense that it is just impossible to imagine trying to find a bug in this code or change it in some way to fix it. Like, just especially interesting. Num less than 91. I'll have to ask them what that means. All right. Snap, by the way, it's a great programming language. I enjoy it a lot. Unless you do recursion, but visually. Anyway, all right. Now, one last little note about complexity and its definition. So it also depends, in John's view, on how often a piece of code is modified. So a system may have a few pieces that are highly complex. Like, for example, it has like a Runge-Kutta solver for like ordinary differential equations because it needs to simulate some thermodynamic yada, 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 right? But if nobody ever really looks at that code, then the overall impact on the complexity of the system is minimal. So he says, if you want, you can write it out as a math equation. So we could say that the total complexity is the complexity of each part times the time spent on each part. Say, where time is like someone needs to maintain the ordinary differential equation solver or whatever, we just sum that. So if there's pieces that are rarely modified but are highly complex, maybe that's okay. Just a thought. All right. Just figured I'd mention it. That was kind of cute. Okay, so where does complexity come from? You guys have some insight into this, but I'll tell you first I'll tell you some symptoms. I'll tell you some causes, and then I'd be kind of curious to hear some anecdotes if anybody has any. So Oosterhout, he describes 3 symptoms of complexity, signs that your code is becoming bad, complex. So the first is change amplification. So if it's the case that a simple change requires you to modify lots of pieces, then your code's getting complicated. So that bad KD tree we saw earlier was an example of that. If I needed to change anything, I have to do it in lots of places. And this happens whenever you, for example, say, oh, well, I have this case, and then I'm going to copy and paste it somewhere else. I have 2 copies of the method with just like some minus sign flipped or whatever. That's an example of complexity creeping into your code. Another is cognitive load. So this is how much you need to know in order to make some kind of a change. Now, this is not the same thing as a number of lines of code. It's often the case that more lines of code is simpler because it's more narrative. That's why I often define variables on one line and then use them elsewhere. You can do it in one line, but I find the code much simpler if it has a name. In some cases, you may incur a small performance hit, but in modern compilers in Java, that stuff mostly gets optimized out anyway. Incidentally, someone asked, why don't we use plus plus or minus minus on Piazza recently? So you can do it, but you'll notice I often use plus equals 1. The reason I don't really like plus plus is because it allows you to do things like, let's comment this out. So it allows you to do things like return x plus plus, whatever. So if x is some variable, this says I want to both increment and calculate the result of x plus 1, and I'm going to return the value before the change actually happens. So that's something that's comprehensible to humans. I mean, I just said it so fast that you didn't really get a chance to digest it. So it's not so crazy, but I still think that it introduces a new possibility where bugs can arise. And actually, one thing that I really wish I had done, especially inspired by Homework 4, is change the setup for IntelliJ so that using equals versus dot equals was some kind of very glaring warning. Because I know, who here had that happen to them on Homework 4 out of curiosity? Yeah, where you use equals and then you spend hours of your life realizing, oh, oops. So, next semester maybe I'll set up an IntelliJ warning. Yeah. Yeah, a lot of them. Yep. So, incidentally, that's why I find plus plus difficult. That's actually an example of cognitive load to some degree. This idea that there's just more stuff to think about. And one of the reasons I really like Java as a programming language is the static types constrain your thinking. When you go back to writing Python code, if you haven't in a while, you'll feel a little like, it's like scary. It's like waking up on the beach in the middle of the night. You know, you're like, how did I get here? You don't know where anything is. There's functions. They're giving you stuff. You don't know. It just feels bad to me. And every time I come back to a statically typed language, I feel like I'm home. All right. Reduces cognitive load. Then the last he describes is something he calls unknown unknowns. Now, this is a bit of a slippery definition that I will say I don't fully understand, but he says it's the worst type of complexity. The difference here is that unknown unknowns are when it's not even clear what you need to know in order to make modifications. Now, I can certainly appreciate that, where I have downloaded some tool. Actually, somebody came to my office hours who was working on a tool to do gaze tracking. So for people who can't move their arms and legs, it's hard to use a computer, but not impossible, because most people can still move their eyes. So you can look around, you can blink, and if you have a camera tracking somebody's eyes, well, then they can actually manipulate the physical universe around them, because they can look around, blink in certain locations, and in principle, it's possible to control a mouse cursor. And if you're somebody who is locked in to that degree, it's quite freeing to be able to interact with the world. Even if it's kind of low bandwidth, it's better than nothing. And so the student who I was talking to in office hours said, how do I take this very complicated open source gaze tracking software and make it so that I can click when I blink? And here, it's actually, this is not a flaw with the software system, but just the fact that it's a difficult task. There's a significant unknown. How do you take this thing and somehow control the mouse cursor? And that's something that's very difficult to grapple with in systems. All right. So what about good systems? What features do they have that help us avoid these symptoms? Well, the main one, I love this term, is that he says a system should be ideally obvious. So in a good design, the system is obvious. In an obvious system, to make a change, you can easily, quickly understand what you need to change. You understand how the code works. And if you want to do something like change the font size or make it so that the user doesn't have to log in every 15 days, but only every 30 days into whatever, their two-factor authentication or whatever, then ideally in an obvious system, it's just easy. They don't have to think about it. And what's more is that they should feel pretty good that the change will work, even though they don't read much code. So examples of this would be you have a table of constants, and you just go into the constants that are well labeled, and you say, instead of 15, 30. That's an example of an obvious system. Okay. So why are systems not obvious? Where does complexity come from? Well, I should note that every software system starts out beautiful, pure, and clean, right? It's just a blank file. The problem is, though, that as you work with code, it slowly gets uglier and uglier. And this is almost an inevitable feature of every program I have personally ever written. And what happens basically is that you introduce these little complexities a bit at a time. And some complexity is inevitable, right? If you're building a system that's able to track the gaze of a human being, it is going to have some complexity to it, because that's just inherently a complicated task. Now, what happens, though, as you build a software system is that you make these hundreds or thousands of small dependencies and obscurities that are going to build up over time. And eventually, there's going to be so many small issues that every possible change is affected by a lot of them. So this incremental process of creeping complexity is why it's so hard to keep complexity under control. You've done this when you're writing programs where you're working on it, you're adding little bits of changes to fix some corner case, and eventually your code becomes, it turns into this KD tree, right? This author didn't set out to write something like this, but as they added pieces, it's like, I could go back and refactor, but I know if I just add another if statement, I'm pretty sure it'll work. So Oosterhout says, rather than ever letting yourself do this, you should have a zero tolerance philosophy. And I think that's actually a good message when you're building real software. Arguably not reasonable in the middle of a semester when you're busy, but hey, it's a good strategy for the real world. All right. So I'm rounding out some thoughts. And we're going to do a little exercise soon. So let's talk about what he calls strategic versus tactical programming. So out of all the programming you've ever done, I'd say that it's pretty much all tactical. So your goal was to get something working, like introduce a new feature or fix a bug. Like this is what you do. So that may seem like kind of a silly criticism, because having code that works is a good thing. Like, why is it bad to optimize for working code? And you can probably see this coming, but the problem is that if you do this, you don't spend time thinking about the design, and you introduce these little complexities, like I need 2 copies of a method that do similar things. And every one of those complexities always feels fine, right? You're like, this is going to make my code work. It'll do this extra thing. But eventually, when you do work on these problems, you start to feel the weight. You could step back and fix it. The author of KD Tree here could have stepped back and changed things up. But why don't you? Well, because you just need to make a few more changes that you could submit the autograder, and then you could do everything else that you want to do in your life, right? So the problem, if you take that with you forwards, and maybe even now while you're working on projects, is that you end up building so much complexity into your system that you can't really keep track of it. And eventually, you end up adding even more complexity to deal with the original complexity, and it snowballs. So in Project 3, good news, I will give you a chance to build something big enough that you will feel the complexity creeping, because you're going to build something from scratch, and you should see it and feel this menacing complexity. Now, the good news is that the system is just small enough that I think you can get through it without a bad time, but you will feel the bad time all around you. Okay? All right. So it's kind of like painting yourself into a corner and then like tossing a bunch of landmines. And then you can quit, and you don't have to worry about it again. Okay. Yeah. All right. Yeah. Oh, yes. Thank you. Cool. All right. I'll go back. Okay. All right. Anyway. No luck. Mysterious, right? Let's do that. Okay, hold on. Yeah, I meant to... Yeah. We were making the slides animated earlier, but they didn't show up. Okay, let's go. Project 2C is out. It is due on Wednesday. Do we have any visitors for Cal Day? Okay, good. No, okay. I gotta scroll back over. Okay. Okay. Is it worth it, Itai? We'll find out. That's fine. Okay, let's see if it happens. Whatever. All right. So he goes on to say that rather than be tactical, the first step, okay, maybe there's one sentence that I want you to take home today. The first step towards becoming a good software designer is to realize that working code isn't enough. Actually, what really matters when you're building real software, not necessarily 61A, B, or C, or whatever other projects, but when you're building real systems that need to last, the most important thing is the long-term structure of the system. Because getting it working, I mean, it might take an extra day or two to get it working if you're building things out in a strategic and carefully thought-out manner, but you will get much better benefits in the long term. He goes on. He also says, though, that again, remember he has this zero-tolerance policy, which I think is a great idea, and I try to keep that with me when we build graders. I feel like our auto-grader infrastructure is generally pretty good. Doesn't break on a fundamental level. Though, the homework for auto-grader was definitely done tactically. Sorry. Anyway. Strategic programming, of course, takes lots of time investment, and again, it will seem mysterious and hard, but Project 3 will give you a chance to see what's going on. All right. So we give you a couple suggestions. Well, it feels like it's going a little long now, but I hope you're still enjoying it. So he goes on to say that, and I mean, this is my interpretation, so I agree with this. But so when you're actually building something out, what do you do that's better? Well, rather than, and I think this is a great idea, rather than just implementing the first idea that you come up with and just running with it until you're done, I would say come up with a few different ideas and maybe start implementing a few of them, just a little bit at a time. And when you feel like you've found something that feels truly clean, then commit. Now, often, I don't know if this has happened to you in office hours, we are working on one way to solve a problem, like, say, A-star or KD tree or whatever, and you're debugging, and you've spent 4 hours trying to debug this compact little piece of code where you know there's something wrong, but you're not sure quite what is wrong. But sometimes really the best solution is take that file, comment everything out, and then just redo it from a fresh perspective. Because what you're going to do is approach it from a slightly different angle, and doing it from a clean and informed perspective will get you better results. Okay, so that's kind of a different version of this, that rather than just trying as hard as possible to get your first implementation working, sometimes it's best to set it aside. And then in real systems, including Project 3, you should try and imagine how things might need to change in the future. And I'll give some examples when we do our exercise. Okay. Now again, I must note that this is extremely hard. Me saying, well, just plan ahead, I think is a little dangerous, because no matter what you do, there will always be mistakes. We've talked about the idea, for example, in Project 3 of having a design document where you have to specify all the dependencies and classes and whatever else. But I find it next to impossible to actually sit down and do something like that without programming. And especially in 61B, I think it's tough. So I guess what I would say when you're doing Project 3 is avoid the temptation to patch around the mistakes that you do make in your design. Instead, I would actually take the time to step back and fix what's wrong. So, just tiny example is S-lists. We had that special case, and we could have if statements, but I think Sentinel nodes were a cooler idea. Okay. Now, quick note from an industry perspective before we do our exercise. He talks about how different companies have different cultures. And he describes that as a startup, when Facebook was very small, which was not that long ago, Facebook embraced what he calls tactical programming. They have the slogan, move fast and break things, and basically you would get hired, and it would be pretty normal for people to be building code and pushing it to the live site within the first week on the job, code that people are actually interacting with. And so that's great, because when you're an engineer, it feels like you actually have control. You're just an employee, but I can actually change the way that messages are sent, or the way that the feed is displayed, or what shows up in the feed. And it also means the development is really fast in the short term, because you don't have to go through more complex code review processes or whatever else. Now, clearly, Facebook was incredibly successful, but its code base was noted as a mess. So Oosterhout, having the inside scoop, says that their code base was incomprehensible, unstable, few comments or tests, and painful to work with, which made working there less fun. Now, eventually, they changed the company programming culture, and their motto became move fast with stable infra, which certainly sounds less sexy, but I guess makes people's jobs better. Now, interesting note, and we'll talk about this in another one of our Friday lectures, is the impact of how companies make decisions about what to work on. And so Facebook, you could argue that their general attitude in life, this same kind of theme has done great harm to the world, arguably. I don't know. We'll talk in a future lecture, and I'll get some of your perspectives. But obviously, they built this very powerful tool that has been released to the world and arguably has done damage. Now, by contrast, there are other companies that have a more strategic culture. So he points out Google and VMware. And I will say that I've had this vision, but I have not yet done so, of interning at Google or Facebook or something some summer, because it seems fun. I have a friend at Google who I was going to intern with a summer ago, but then I didn't want to commute to Mountain View from here because it's too far, plus the baby. Anyway, but he says that, because I wanted to know about their software practices, because I teach this class, and I want to have more real-world stuff to bring you, because it's been a while. And so he says Google, company known for its strategic approach to software, and VMware, they place a heavy emphasis on high-quality code and good design. They build sophisticated products that solve complex problems with reliable software systems. That's especially true if you're familiar with VMware, where they write software that literally emulates operating systems inside of other operating systems. Very technical and difficult work. And so these companies' strong technical cultures are well known in Silicon Valley, and few companies can compete with them to hire the top technical talent, whoever those people are. Now, real-world projects and companies, they succeed with either approach. Obviously, Facebook is an enormously successful company, even though its original technical roots were maybe a little dicier. Osterhout, though, then says, I think it'd be more fun to work somewhere with a nice code base, so I guess if you trust him, you should work at Google and not Facebook, but I don't know. Anyway, yeah. All right. So, complexity. Okay. Let's see. Do I want to just jump in? Yeah. All right. I'm just going to say one more thing. This slide used to be earlier. Oopsie. Anyway. So where did complexity come from? He gives two examples. Dependencies and obscurity. Okay? So, see, he even has an example. All right, I'm getting rid of that slide. We're going to come back to that one later. Anyway, Cal Day. Thanks for visiting. Cool. All right. So now what we're going to do is we are going to try and do an exercise to make obvious code. So one of the most important ways to make your code obvious is to decompose it into separate parts, which are often implemented as helper methods or subclasses or whatever else. So I'm going to try an exercise which is inspired by bear maps, and this is a very simplified version of something you'll do in that project, but you might find it helpful to think about this. So the problem I'm giving you, arbitrary problem of the day, is that we have a two-dimensional space that goes from 0 to max x and 0 to max y. So if max x is 100 and max y is 100, this is the space. Okay? It's small. It's finite. Now let's say we break that space up into subspaces, in this case 16 of them, and I label them AA through DD according to the pattern shown. Okay? Now, let's say I want to find all of the regions that overlap a query rectangle. This is very closely related to the rastering task on the assignment, though it's different enough that I'm not spoiling anything, and it's easier in certain ways. So for example, if I have the rectangle 20, 90, so 20 over, 90 up, and 40, 60, I end up with, the answer to this problem would be AA, AB, BA, BB. And I want to give the answer in level order, so AA, AB, BA, BB. So solving this problem, this is fascinating to me. Last semester, at the very end of 61B, after, 30 weeks or 28 weeks of an intense Berkeley education, I was very surprised to see that a lot of people ran into a bit of a brick wall, not with this problem, but something kind of similar. And I think a lot of it really boiled down to jumping in and not thinking ahead. Because I was surprised. I figured this subproblem is going to be no problem for my kids. They're going to do good. And a lot of people did fine, but it was just very interesting. And I think my main advice is to think very carefully before jumping in. So what I'd like you to do is let's imagine we're writing this code above. So there's no rectangle, there's no AA, there's no BB. All that stuff is just something you're going to have to produce, right? So all you have is a function that takes x1, y1, x2, y2. And ultimately, you're going to have to return, for this specific example, AA, AB, BA, BB. The point is that the starter code is very simple. So let's suppose you're trying to solve this code above. I'd like you to try and come up with an approach or two to solve this. And what are some helper methods you might imagine are useful? Okay? So I'm going to leave this up here, and I will give you guys we got time. Let's do 2.5 minutes of pondering helper methods or approaches you might use, just at a very high level, and then I'll talk a little bit about what you might come up with. Okay? So give it a shot. Try and figure out how you'd solve this problem. Now, one thing you'll note is it's very hard to solve these problems without a computer to try out a little bit of stuff, but give it a shot. Okay, I would be curious to know if anybody has specific helper functions you want to suggest or approaches. Either way, helper functions, things that might be useful. Yeah. Okay, got it. So we'll call this thing like x column, and you give it an x. And you could, in principle, do this. So, for example, if you have 23, so x column, I'll give you some input-output examples. So we've got 23 would give you what? All right, let's do like 15. You give it 15, and what does it return? They're 25 each, I guess. Max x divided by 4 each. 0, like 33 would give you 1, 51 would give you 2, 76 would give you 4, something like that. Some examples. Okay, I think that's a great example of a helper method that might be useful. Others? Yeah. Out of bounds, that's interesting. So, I don't know, private Boolean, I'll do inbounds. What do you want? Oh, this should really be a double, by the way. Double x, double y. Okay, so that could be handy because you could throw exceptions. So returns false if xy is outside max x, max y. Okay, I know that's not strictly speaking true. We got to say the other coordinate, the 0, but I'm not going to do it. Okay, so we could write that. Okay, other helper methods that might be useful. Yeah. What do you mean the vertices of the rectangle? 2090. Yeah. Oh, the other two. Okay, so that's interesting. So you could write, for example, so let's say you wanted to do that. What type would that return? So I want to return like upper right, where I give it the x1 double x, or y1 double x2 double y2. Okay, so what would it return, this upper right function? So a list, okay, so a list of, let's say, doubles. Okay, this is a really interesting discussion. So returns a list of length 2. Is that right? Oh, it's actually all. Okay, I'm going to recommend that what you would want really here is something like, I don't know, like 0.2D or something like that. So you could give a type that returns the upper right. Though, funny story, it turns out that, I guess I'll import whatever this thing is. It turns out that this is not actually a useful method, but it's unclear, right? At least the approaches I might have. Yeah. Got it. So something like string. Let's call it like a box string. You give it double x1, double y1, double x2, double y2. And this will tell you in a specific location, what is that going to be? So you give it like this point, and it'll give you AA back. Okay, last thing I want to ask is, what are some approaches? If you have all these helper methods, what's something you could do to solve the problem? What do you think? Yeah. So smallest x, which will always be, let's say that this is always the upper left, so let's say it's x1. Yep. Okay, which will be here. So I got the smallest and the largest x value. Great. Do the same thing for y. So you have a range of y values. Yep. Yeah, so you basically create a list, or you know the start x, the end x, the start y, the end y, and you just iterate over. So that's one approach, which I think is the more natural approach. The other approach that you may attempt, but is not a good idea on Project 2C, is let's just iterate over every possible box and say, is it valid? I don't like that approach as much. It's more complicated. So that approach is, let's look at AA, AB, AC, AD, and for each box, see if it intersects the rectangle. I think it is more natural just to iterate only those rectangles you know are good. I know that's a little vague, but the big picture here is that these ideas, having these helper methods, and, mind you, writing tests to verify that they work, these are better building blocks, better types of abstractions that will make your code more obvious. And so when you work on your raster, when you do Project 2C, strive for obvious code. It'll make your life better. It'll make the TAs happier in office hours. All right. Thank you, everybody. I hope you enjoyed this weird lecture. There'll be 2 more weird lectures to come. All right. I think it was successful.